rod 0 to L. This is the y-axis, this is the x-axis, and this is the rod. So this is L here, and we need the potential at an arbitrary point P. Okay, we need to find what Vx at some distance x. We need to find what the potential is. And since this is a finite rod, we can take our reference point, so we can say that V reference is at infinity to be 0, because far away your potential drops as 1 over r, so at far away you will get 0 potential. And this carries a charge of lambda, meaning lambda coulombs per meter. Because we know that the potential for a line charge is V equal 1 over 4 pi epsilon, right? We have a line charge here, so we'd have to integrate lambda at r prime, okay, over the separation vector dl prime. This is what you need. So basically you have to take, so your separation vector is, you have to take a slice here of this, right? So at a distance, let's say x prime.
So it's P minus x prime.
X prime, right? Yeah, and then your separation distance would go from here to point P. Yeah, and so that would be x minus x prime.
Or P minus x prime.
P is at x 0 0.
No, it's here.
Yeah, P. At x away from the origin.
Yeah, x minus x prime.
Yeah, and so this integral becomes 1 over 4 pi epsilon integral lambda, okay, over x minus x prime. Now you are integrating this. What's dl? It's x prime because it's every piece along the rod.
Yeah.
So this would be dx prime, and we are integrating from the beginning of the rod 0 to L.
Right. Yeah. I forgot that the dx is actually
right. So if we do this integral here, let me see. So lambda is uniform, so it can come outside the integral. So we get I'm gonna take this minus 1 out here, okay, and this becomes 1 over x prime minus x. So I switch them so I can get x prime first, dx prime. Now x in this context is a fixed point, so x is a number. Yeah. Okay, and we are integrating from 0 to L, so this would be minus lambda over 4 pi epsilon. Technically I'm supposed to begin this with V minus V reference, but because V reference is 0, right, I would get away with just V. So back to here, lambda 0, and this would be ln x prime minus x from 0 to L, and we would get ln. So the bounds are for x prime, not for x. So L minus x, evaluating upper bound, minus ln absolute value of minus x, if we plug in 0, and so here we would get our potential to be lambda over 4 pi epsilon. Now this is ln the first over the second, but because I switched the sign, they switch. So this becomes ln minus x over ln l minus x. And
shouldn't it be ln positive x over ln l minus x?
where?
It wouldn't it, because
There's two ways for the electric field. There's two ways to do it.
I took the negative.
You could either take part A,
That's,
the answer to part A, assuming it's the correct answer, and find the gradient, right? Because the electric field,
the negative gradient.
is negative the gradient of V. Okay, but for this way, you need to make sure that you have the right answer in A. Otherwise, part B would be long. If someone has doubts on part A, you could just integrate and find the electric field. Okay, so this is along the x-axis, right? There's no y dependence or z. So this is minus d over dx, or we could just do straight derivative, whatever. Right? Lambda over 4 pi epsilon ln minus x okay, so let's see, we have to differentiate this, correct? So and this would be the x direction. Okay, so E would be integral of ln is 1 over, so this would be L minus x over, why did it quit on me?
We want the derivative of
1 over, yeah? So 1 over what's inside, then you do chain rule on the inside, because the inside is also a function of x. So you have to do chain rule on the inside, no?
So it's the derivative of what's inside over what's inside. Well, it's the derivative of the x over x minus L. And then I divided that by x over
this is in the x direction. Let me say minus lambda over 4 pi epsilon, right? Now if you differentiate this with respect to x, you get 1 over, so you just switch this, right? Times, you need the quotient rule to find the derivative of the inside. So this would be
actually mine's different because I did negative and I flipped it over, so I got x minus L over x, and so I just turned that into 1 minus L over x, and the derivative of that would be
yeah. Now actually you're right, we have to be careful here because x is larger than L. So we might have to actually adjust that first answer here. If x, because where point P is larger than L, right? Then when we take the absolute value of this, it's actually let me rewrite this. So V would be lambda over 4 pi epsilon. I mean, we have an absolute value, it's safe, but it's better for derivative's sake to just get rid of it.
Yeah, I see what you mean. Although it doesn't work. Well, although that, my thing did work because the
right,
L is less.
and this would be x now because x is positive, because it's on the right hand side, and this would be x minus L if you want to be really technical about this. So here we have to be careful with that derivative. So let me change this around. So this is
Although
x
I
over x minus L.
I actually have this negative, like I have negative of this.
Which switches these two. Say that again.
I have actually negative of that, and I flipped this over.
Yeah, that's fine. That doesn't
So
matter.
I don't need the quotient rule. I just did 1 minus L.
Oh yeah, you could do that too. We should both get the same answer. That shouldn't matter. Yeah. Yeah, you could sacrifice. You could flip this minus sign. I agree. You could make this.
Yeah, I did that.
And then this becomes d over dx of ln x minus L over x. Right, that's what you're saying. And this is all in the x direction. Yeah. Okay, well, let's see what we get here. Lambda over 4 pi epsilon. This is when you flip it, it becomes x over x minus L. And then this is just x over x, which is 1 minus L over x, right? So when you take the derivative, you get this is going to be 1 L over x squared, right, in the x direction. And then if you cancel out, if you cross out an x, finally the electric field will be lambda, right, L over 4 pi epsilon times 1 over x times x minus L. Okay, and this is all in the x direction.
Yes, that's what I got.
Yeah.
I factored in the x. I did x squared minus xl. So yeah, it's the same thing. That's what I got.
Yeah, you got the same answer.
Yep.
Okay, so this would be the electric field, and the first one we found would be the potential due to this finite line of charge at point P on the x-axis.